Now consider detection limit. Okay, depending on the atomization method, detection limit quite different. Okay, first we have to define the detection limit. The concentration of an element that gives a signal equal to two times, okay, two times the peak-to-peak noise level of the baseline. Yeah, that's the detection limit. Here, look at that. This one, definitely, this is a noise. Yeah, this is a peak-to-peak noise level. Okay, and the signal must be at least two times the peak-to-peak noise level. Yeah? So this signal here is more than two times the peak-to-peak noise level. Okay, so but if the signal is smaller than two times the peak noise, then we ignore they may not be the signal looking like not the peak may not be a real signal. Okay, look at this periodic table. Yeah? So virtually, this atomic absorption or atom emission spectroscopy applies to virtually to every element. Okay, except maybe here the hydrogen here. Okay, and carbon, with nitrogen, oxygen, fluorine, and also this inert gases. They are not detected by these techniques. Okay, but there are almost every you know the elements could be detected by this technique. So this atomization based techniques you know very widely applicable. Okay, here how to read these values here. For example, ion, it has four numbers: 1, 2, 3, 4. The first one is inductively coupled plasma emission. Yeah, that's the detection limit. The unit is nanogram per gram. Okay, nanogram per gram is what? That's the ppb. Okay, and this one, the second one is flame atomic absorption. You see, absorption spectroscopy is always less sensitive than the emission spectroscopy. Okay, so flame atomic absorption is the detection limit is quite low, but compared to other the methods, is uh, limit detection limit is rather high. Okay, and the third one is the graphite furnace atomic absorption. Yeah, it's better than the inductively coupled plasma emission. Okay, you'll see why. Okay? In graphite furnace, the atomic species, would stay there longer. Okay, longer than the ICP. But best one is given by inductively coupled plasma and coupled with mass spectrometry. Okay, uh, these two independent techniques are combined here. Okay, yeah. All right. So here the detection limit for furnaces is typically two orders of magnitude lower than that observed with a flame. This one atomic absorption here. Okay, two orders of magnitude better. Okay, because the sample is confined in a small volume of the furnace for a relatively long time. Okay, that's why. Okay, now let's consider the interference. Okay, atomic absorption or emission techniques are not perfect. Okay, there are interferences from many uh, many interferences. Okay, interference is any effect that changes the signal while analyte concentration remains unchanged. Okay, um, so it is important to minimize the interference effect. Okay, interference can be corrected by removing the source of interference, okay, or by preparing standards that exhibit the same interference. Okay, yeah, and by comparing your sample signal with that of standards. Yeah, so we can maybe we can deal with this interference. There are three types of interferences. Okay, first one is a spectral interference, which is the unwanted signals overlapping unaligned signal. Okay, And second one is a chemical interference. Uh, Chemical reactions decreasing the concentration of analyte atoms. And last one is ionization interference. Ionization of analyte atoms decreasing the concentration of neutral atoms. Okay, yeah, in the atomization based techniques, we simply assume that all the elements are atomized, not ionized. Okay, but in many cases, ionization, not atomization, take place. Okay, that interfere the signal. Okay, let's consider from the first one. Yeah, spectral interference. Let's look at this, the atomic emission spectrum. Okay, uh, this arsenic. This is a species of your interest. Okay, it generate, it emits, the electromagnetic radiation at 228.812. Okay, but when the sample contains the cadmium, also cadmium emits the radiation here. Okay, and its wavelength is very similar, 228.802. So the difference is only 0.01 nanometer. Okay, wow, that is a real small difference. Okay, yeah. And so the difference is so small, so you need a very high resolution spectrometers. Okay, and so here this part. Okay, this part is a little bit overlapped. Okay, so exact determination of arsenic is not possible. Okay, how do you solve this problem? Yeah, not the best one way is to use what higher resolution spectrometers. Okay, and if you use higher resolution spectrometers, and then this one maybe this cadmium peaks may appear here, and then this one arsenic peak is appear here. Okay, in other words, with the high resolution spectrometers, this peak, the this width will be decreased. Okay, yeah, that's the best way. Yeah, with sufficiently high resolution, peaks are separated and there is no interference. Okay, that's the best way. And look at this figure here. Well, this no, the figure is from the emission spectrum of this high temperature superconductor. Okay, yttrium, barium, 2, copper 307. Okay, this is a very famous high temperature superconductor. The superconductor means that the the at below the certain temperature, the resistance becomes zero, absolutely zero. A superconductor means the material that don't have any resistance. Okay, and this is very famous, and where yttrium and barium, and also this is a barium peak. They are well resolved. Okay, but here in this the wavelength region, beyond 580 to about 620 nanometers, these peaks are quite thick. Okay, and why is that? This is from the yttrium and oxygen. This one, this kind of a molecular peak. Okay, molecular emission lines are broader than atomic emission. Okay, yeah. So this is a really problem. Okay, yeah. So uh, uh, to avoid this kind of a molecular peak, right? So these molecules should be atomized so that the peaks becomes very sharp. Okay, yeah. Yeah, that's the spectral interference. Okay, this part, this barium peak, and this one, this peaks from YO molecular species overlap here. Okay, and another interference is from chemical interference. Okay, it is caused by any component of the sample that decreases the extent of atomization of analyte. Okay, you know, uh, in atomization, the best spectroscopy, the important thing is to atomize the element completely. Okay, otherwise, less atomization uh, decreases the intensity. Okay, but unfortunately, some chemicals now hinder the atomization. Okay, for example, the sulfate and phosphate hinder the atomization of calcium ion. Okay, uh, perhaps by forming a non-volatile salt. Okay, you see, this one is a negatively charged, and this is positively charged. So they form kind of what compound. Okay, so you have to avoid this chemical interference. How? You can use a releasing agent. Okay, a releasing agent is chemicals added to a sample to decrease chemical interference. Okay, for example, EDTA and 8 hydroxyquinoline, okay, protects calcium ion from interference by this sulfate and phosphate ions. Do you know the principle behind this uh, EDTA and 8 hydroxyquinoline? Okay, yeah, principle is that EDTA and 8 hydroxyquinoline, they are organic compounds that forms what is the coordination bond with this calcium ion. Okay, so that means what? Although the sulfate and phosphate ions now, you know, bind this calcium ions, and then in the presence of EDTA or this 8-hydroxyquinoline, bind. Let me see. The formation constant with EDTA is much higher than these ions. Okay, so EDTA now, to take the calcium ions from the sulfate or and the phosphate. Okay, and then at the elevated temperature, EDTA now is removed, because this is all is made of organic. I mean, this is organic species. Okay, and then calcium ions now, you know, become atoms. Atomization is a more the perfect, yeah, in the presence of the sulfate and phosphate. Okay, yeah, this is the chelation. Okay, chelation, chelating calcium ion with EDTA. Okay, now avoids this chemical interference. Okay, and also you can use this lanthanum, the ion. Yeah, this is also a releasing agent, apparently because it preferentially reacts with the phosphate and frees the calcium. Okay, let's assume this calcium ion now forms the calcium phosphate. Okay, but lanthanum phosphate is much stronger. Yeah, so in the presence of lanthanum, lanthanum now replaces this calcium ion. Okay, so calcium ion is freed, from this phosphate ion. Okay, so this calcium ion easily atomized. Okay, a fuel-rich flame reduces certain oxidized analyte species that would otherwise hinder atomization. Okay, so if you use fuel-rich flame, okay, and then oxidized analyte species, uh, yeah, so it reduces the amount of oxidized analyte species. In the presence of this oxidized analyte species, atomization may be hindered. Okay, so this is another way, which is using the fuel-rich flame. Okay, and also the higher flame temperature eliminates many kinds of chemical interference. Okay, yeah. So to avoid this kind of chemical interference, okay, so simply increase the flame temperature under such a high temperature, all almost every element uh, can be atomized. All right. Okay, third interference type is ionization interference. A problem in the analysis of alkaline metals, okay, at relatively low temperature, and in the analysis of other elements at higher temperature. Yeah. For example, in the gas phase ionization reaction, this one, uh, this is atomized metal, okay, and uh, in, which is in the gas phase, but it undergoes ionization to this metal ion by ejecting the electrons, okay, here. So since it undergoes this ionization, that reduces the signal, okay. So for this reaction we can write this chemical um, equilibrium constant, okay. Ions have energy levels different from those of neutral atoms, so the Z signal is decreased, okay. This is very important. Okay, once you may say, what hmm? what's the problem of ionization, okay. So this if ionized, if the atom is ionized, the energy levels become different. So although we get some very strong spectral peak, but we are sure that peak is from this the metal atom or from metal ion, okay. Because one species have many atomic emission spectral lines, okay. So it is important to be sure that the elements are atomized, not ionized, okay. That's very important. Alkaline metals have low ionization potentials, yeah. This is quite well known, okay. That means what with low frequency electromagnetic radiation, atomic alkaline metals are easily ionized, okay. They are most extensively ionized, okay. This one, alkaline metals, at 2450 Kelvin and a pressure of 0 0.1 Pascal, sodium is 5% ionized, okay. Oh, this is a lot, right? This is a great percent, okay. 5% ionized. Yeah. So this problem, ionization interference problem, is mostly for the alkaline metals, all right. And so we need an ionization suppressor. Yeah, this suppressor decreases the extent of ionization of an analyte. Okay, so if we add this ionization suppressor, this reaction now moves to equilibrium, moves to the left side. Okay. In the analysis of potassium, this is also alkaline metal. It is recommended that the solutions contain 1000 ppm of cesium chloride, okay, because cesium is more easily ionized than potassium, because cesium this one is the mm, you know it has higher what atomic the number, so this is a bigger, much bigger than the potassium and easily ionized, okay. And so cesium suppresses potassium ionization, okay. Well, cesium is more easily undergoes ionization, so that suppresses potassium ionization. Electrons from cesium ionization moves equilibrium. Okay, here how once cesium ionization takes place, okay, it produces a lot of electrons here. So from here, from this equation, by the Lewis-Chatelier principle, so this one, the concentration of electrons increases, and then this equilibrium moves toward the left side, okay. Yeah, that's how the potassium ionization is suppressed, okay. Very simple, all right.